All right, we're going to continue working problems. Chapter 11, Module 3, the yo-yo. And the problem that I have selected, the yo-yo has a rotational inertia of 950 grams centimeter square and a mass of 120 grams. Its axis radius is 3.2 millimeters and its string is 120 centimeters long. The yo-yo rolls from rest down to the end of the string. What is the magnitude of the linear acceleration? How long does it take to reach the end of the string? As it reaches the end of the string, what are its linear speed, translational kinetic energy, rotational kinetic energy, and angular speed? The book describes a yo-yo as a ball rolling down a 90-degree plane. So we have this formula, A equal to minus G sine theta over 1 plus I, center of mass, over m r squared and this would go to, because minus g, because the sine of theta 90 degrees is just 1 over 1 plus I, center of mass, over m r squared. So A is, what is the magnitude of the linear acceleration? So we're going to have A, acceleration, going to be G, which is just minus 9.8. We know it's going to be in meters per second, so we squared, so we won't worry about that right now. 1 plus center of mass was given to us as 950 grams per centimeter square. 950 grams dot centimeter square. And we know the mass is 120 grams. We're not converting it to kilograms because we have a ratio here and we expect everything to cancel out either anyway. And we're looking for the radius square. Now the radius is 3.2 millimeters, which is equal to 0.003 meters, which would be equal to 0.03 centimeters. We want to keep it in centimeters, so we have 0.03 centimeters, and its R is squared. It's squared. So when we do the math on this, A is equal to 9.8 minus 9.8, and we're gonna have this denominator here. Let's clear everything. 950 divided by 120 times 0.32 squared is equal to 77.3 plus that 1 over there. We'll make it 78.3, and we're going to divide 9.8 divided by 78.3, and we get 0.125 meters per second squared, which is equal to 12.5 centimeters per second squared. So this is the answer to part A. Now B asks, how long does it take to reach the end of the string? So we know that this is going to be a kinematic equation, and we have, let's go with the y, center of mass, is going to equal V sub OT, it's going to be 0 when it starts. And since we know time is going to be positive, we're just going to put a plus sign here and not worry about the direction where the yo-yo is going down. So, because time is going to be positive. So 1/2 angular acceleration t squared. It's not angular acceleration, it's this acceleration, linear acceleration, t squared. And we're going to solve for t. We know that y, center of mass, the length of that is 120 centimeters long. So we go 120 centimeters is equal to 1/2 a t squared. And this will go to t squared is equal to 2 times 120 divided by 12.5. We know this is going to come out in seconds. So t is equal to the square root of 2 times 120 divided by 12.5. That's going to equal 2 times 120 is just 240. Divided by this will give us 4.38 seconds. So How long does it take to reach the end of the string? That's part B, 4.38 seconds. Now C asks, what R is linear speed? So V, one of our kinematic equations, is equal to V sub O, which is 0, plus the acceleration times time. We got both of those. So the acceleration is 12.5 centimeters per second squared times 4.38 seconds, and that's going to equal 54.75 centimeters per second. So that's the answer to part C. D, translational kinetic energy. So the translational kinetic energy, K, is equal 1/2 mv squared. So K is going to equal 1/2 0.120 kilograms, converting this 120 grams to kilograms, times V squared, which is, we calculated that to be 54.75 centimeters. We'll just say 0.547 meters squared. And when we multiply this, 0.5 times 0.120 times 0.547 squared is going to equal 0.0179 joules. So that can be written a little better, which is a scientific notation. We could write it as 1.79 times 10 to the minus 2 joules. So that's the answer to translational kinetic energy. E, rotational kinetic energy. So E, K is going to equal to 1/2 I, which is given, omega squared. Now we have smooth rolling, which means that this omega square, we can do this. V is equal to omega R. So omega is equal to V over R. We want to substitute that into this